Hi, it's time for another math easy solution. Time to discuss further into differential equations and now look at the topic of separable equations. Basically, in my earlier videos, we looked at the first order differential equations from a geometric point of view in terms of direction fields, and also from a numerical point of view in terms of Euler's method. And both of these were pretty much approximations to the solutions. But what about the symbolic point of view? In other words, it would be nice to have an explicit formula for a solution of a differential equation as opposed to simply an approximation as with the previous methods that I covered in my earlier videos. But unfortunately, as explained also earlier, this is not always possible to find an explicit formula for the solution. But there are certain types of differential equations that can be solved explicitly. In this video, I'll take a look at one specific type, and that one is a separable equation is basically what I'm going to look at, and it's basically a first order differential equation in which the expression dy over dx can be factored as a function of x times or multiplied by a function of y. In other words, it can be written in the form, in this form right here, dy over dx is equal to, so this is the differential equation, and you could write this as a function of x, g of x, times by a function of y. And basically the name separable comes from the fact that the expression on the right side can be separated into a function of x, as here g of x, and as a function of y, this f of y. So that's the whole idea of separable equations. And equivalently, if f of y is not equal to 0 at any point, then what we can do is we could just write generally dy over dy over dx, write this a bit neater, is equal to, we'll write g of x, and then we'll write h of y at the bottom, where basically this function h of y is equal to 1 over f of y, and that's why we had if f of y is not equal to 0, so at any point it's not equal to 0, we could have it like this, so that you don't have h of y undefined, because 1 divided by 0 goes to infinity or undefined, etc. And now the reason we're writing it like this h of y function, is because now we could separate these and make it look like basically in a differential form. I'll write that soon. So basically to solve this equation, we first rewrite it in a differential form. So what we're doing right here is we're going to separate the two functions on the right side so that the left and right sides of this whole equation will only have either all the x's or all the y's on either side. So we're going to move this over here and move the dx over here. So what we end up getting is a h of y dy is equal to g of x dx, like that. And now what we end up having is, again, as I stated, all the y's are on one side of the equation and all the x's are on the other side. Then we basically integrate both sides of the equation. So if we would take the integral, so we have, let's just write this down first, h of y dy is equal to g of x dx. So what we could do is take the integral like that. And the reason we're taking integrals is because we want to get rid of this dy and dx's. So, and this, what this equation tells us now is that this equation defines y implicitly as a function of x. This is implicitly saying that y is, you could write it as a function of x, because when you take the integral, you're going to have a bunch of y's and a bunch of x's on here, and you just solve for it. So that's implicitly, but in some cases we can actually solve for y in terms of x explicitly. And that depends again how complex the functions on either side are. And going further, we can justify this procedure by working backwards by applying the chain rule. Basically, just to show that going from here, we can go back all the way there, following following mathematical procedure. In other words, it's pretty much a check or a clarification of this procedure. So it's pretty much deriving it backwards. So to do that, well, let's just write down our equation right now. Integral of hy dy is equal to the integral of g of x dx. So if we were to take the derivative and apply the chain rule for derivatives, we're not going to change either side, so we're going to take the derivative in terms of x, so by going d over dx on both sides. So we're not changing anything. We're just applying Well, yeah, we're not changing the equation. We're just basically not. Doing the exact same thing on the left side and the right side, so that the values are still the same. So when we take this derivative, but notice on the left side here we have these are in terms of y, but the chain rule again we need to apply because we're taking the derivative in terms of x. So to do that, we need to take the derivative in terms of y multiplied by the derivative in terms of x. So what we end up having here is d over dy of integral of h of y dy, and now all the y's we need to multiply this by the derivative in terms of x, so dy over dx. And the right side here, the derivative of the integral, again it's basically the fundamental theorem of calculus, and my derivations on integral calculus in my earlier videos, if you watch those, is pretty much this is just the integrand. So the derivative of the integral is the integrand, or the function inside the integral that's being integrated. So this equals to g of x. And likewise here, now that it's in terms of y, the derivative, because of the chain rule, this is again the integrand. Because it's integral, derivative of the integral is just the integrand. So this equals to h of y dy over dx. And this equals to g of x. And now we just divide this h of y out. So what we end up getting now is dy over dx is equal to g of x over h of y. And again, where h of y is equal to 1 over f of y, is equals to g of x times f of y. And again, this is exactly where we started off. So that's pretty much here where we started right here. So this shows, again, by applying the chain rule, we could show that this whole procedure follows a mathematical procedure, and we can do this. This is, again, just to double check by working backwards. And now just some interesting thing I want to go over is basically this chain rule whenever we have this integral of a function of a different variable, and we're taking derivative of a different variable. Just to clarify, because I haven't gone over a specific type of that for the chain rule, so basically for clarification, let's just look at a simple example. Clarification. Yeah, let's basically look at let y equals 2x squared. So if we were to take the derivative in terms of x of the integral of y dy, well, if we apply the chain rule, what we end up having is, again, you need to take in terms of y, d over dy, integral of y dy, and then you have to do this multiplied by the chain rule, so d over dx, and dy over dx, where the derivative dy over dx is just equal to y prime, which equals to here just 2x. And again, using the fundamental theorem of calculus, this is just equal to y, so this equals to y times it by dy over dx, which is 2x, and then y is equal to x squared, so this equals 2x squared times 2x, and then the x squared and x becomes x cubed, so what we end up having is 2x cubed. That's the answer, like that. Just to show you there. So that's the answer applying the chain rule method exactly as I did over here. And again, I proved the chain rule in my earlier videos, so make sure to watch that in the link below. All the related videos are in the video description below. So what we can also do, to show that we can solve this rule without applying this exact chain rule or the fundamental theorem of calculus, what we could do is we can also solve. Well, we could also solve it by, well, let's just write this down. So we have our d over dx of integral of y dy. So what we could do is, well, apply our, just switch all the variables first. And I'll show you that the answer is going to be the exact same as our 2x cubed. So d over dx, this is going to be integral of x squared, and then the dy, well, the dy is just going to be, dy is equal to 2x times, move the dx on the other side, 2x dx. So this is going to be 2x dx, which equals 2 d over dx, And now we have this integral, this x squared, that's just 2x cubed dx. And again, fundamental theorem of calculus, this is just the integrand. So this equals to 2x cubed. So we avoided the chain rule, still got the same answer, but now if we avoid this fundamental theorem of calculus, well, we'll get the same answer anyways. I'll just write, we can also, or I'll write, or we could, well, what we could do is just start from this step, so d over dx of the integral of 2x cubed dx, well, let's just take the integral. If you don't trust the fundamental theorem of calculus, well, just take the integral of this, and you're still pretty much using fundamental theorem of calculus. Anyway, so take the integral right here of, this is going to be 2 times, well, the x cubed integral is x4 divided by 4 plus a constant c. And this is the constant. And now taking the derivative of this, well, the derivative of this is simply going to be 2 over 4, and then this x 4, the 4 becomes 4x cubed, and then the constant, that's a 0. The derivative of the constant is 0, and then this 4's cancel. We'd end up having is 2x cubed. So again, this is exactly the same way as all these, and applying this chain rule. And again, I just wanted to go over that just to clarify that why we have this dy over dx. Well, just to show how it's still it's the same thing as if you were to replace all of these variables. So you also have to account for this dy over dx, and that's part of the chain rule. If you're not switching if you're not substituting the variables inside, you need to apply the chain rule. Anyways, again, make sure to watch my earlier videos on the chain rule to learn more, and the fundamental theorem of calculus to learn more about that if you haven't already. Yeah, and now before I finish the video, I just want to go over a brief history on this technique that was used to solve it, basically this separable equation technique, separating and taking the integral. Basically, this technique for solving separable equations was first used by James Bernoulli in 1960 in solving a problem about pendulums, and by Leibniz in a letter to Huygens in 1691. Again, these are all just famous mathematicians. But it was later but it wasn't until 1694 when John Bernoulli, which is James Bernoulli's brother, explained the general method in a paper published in 1694. And again, just a brief history on these Bernoullis and Bernoulli family, and basically Leibniz, on the other hand, I did a brief history already in my previous video, so make sure to watch that. That's also in the link below. And Huygens, I haven't gone over him, but I might do that in a later video, so stay tuned for that. But anyways, James Bernoulli, just go over brief history because this is pretty interesting stuff. James Bernoulli, also known as Jacob or Jacques, lived from 1655 to 1705 and was one of the many prominent mathematicians in the Bernoulli family. He was born in Switzerland and was a major contributor to the early development of the field in the field of probability. And John Bernoulli, brother of James, lived from 1667 to 1748 and was also a prominent mathematician in the Bernoulli family. He's again a very famous family. He was also born in Switzerland and was a major contributor to infinitely small calculus. He was, again, he's also famous for having educated the famous and gifted mathematician Leonard Euler. Again, this was a really famous and prominent mathematician, and also he's the guy that had the Euler's method for numerical approximation of differential equations. Anyways, the Bernoulli family were famous for having produced many notable artists, scientists, and mathematicians, but three in particular, James, John, and another guy, Nicholas. Might do history on him later, but anyways, these became the cornerstones and the foundation of mathematics. Anyways, so that's just a brief history. I thought it would be interesting to include it because, again, these techniques and concepts, it may seem somewhat basic, or in other words, we kind of take this stuff for granted, but it's due to the hard work and pretty much the genius of several people throughout history in mathematics, and And this has far-reaching applications in all of science and physics, engineering, etc. Anyways, that's all for today. If you learned from this pretty interesting video on separable equations, in later videos I'll go over some examples and further videos on that. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math